Okay, in this video, we will talk about most concepts and problems in our lecture. Okay, let's prepare the midterm exam. First of all, we talked about the dot product or inner product here. So if vector is given by v and w like this, it is the actual vector in Rn, then we can calculate the dot product, and it is given by just the summation of multiplication of its coordinate. So if it is the just the vector on R3, then v1, v2, v3, and w is given by w1, w2, w3, then we can calculate vw in a product. The product is given by v1 w1 plus v2 w2 plus v3 w3, like this. And we can say that this is also be calculated like this one. So here, this means that it is the norm of v, and it is just the, I think there must be the root here. Root, yes. Or you can say that it is the norm of a square, like this. So by this equation, we can say that cosine theta is equal to like this. So the theta means V and W is like this, then our angle is theta. So cosine theta is given by like this. So there was the problem like this, find the angle between the vectors. Then in this problem, we find the angle using this formula. Actually, theta can be written as, cosine, arc cosine of this VW and VW. Okay. And, there was the cross product in R3. And as you can see, this holds only in R3. Okay, so let's think about two vectors in R3. And actually, we use ijk. If we use this ijk, this w1, w2, w3 is given by like this. w1 I plus w2 j plus w3k. We can write like this. And this cross product is given by the determinant of this 3 by 3 matrix. And you can calculate it like I times the determinant of this 2 by 2 matrix minus j times v1, v2. Sorry. I think it would be better to write down it. I times v2, v3, w2, w3 minus j times v1, v3, w1, w3 plus k times v1, v2, w1, w2. Okay. This is the cross product. And as you can see here, this cross product, the norm of this cross product is the parallelogram, area of parallelogram. It means that V and W is given by like this. Then if we find the cross product, then the length of the vector is given by this area. Okay. And one important thing is if you take a dot product, then it'll be just the number, scalar. But here, cross product, if you take a cross product, then it is the vector. So, so since this one is a vector, we need the norm here. Okay. And this Since it is the vector, we can take inner product with these two ones. And this, after we calculate this one, because the second calculation is inner product, thus our result must be scalar, okay? After taking the dot product, it must be scalar. Okay, so there is no norm notation, okay, since it is a scalar. So, this is the volume of a parallelepiped. Since our volume is positive number, I think it would be better to use the, you know, it is not norm. It is the, just the absolute value of a scalar. So if we say that the our u is given by like this, then parallelepiped is the um I'm not good at drawing. I have you know it's hard to draw. Yes, this volume is given by this formula. Okay, so there was the problem like they find the volume of the parallelepiped determined by these three vectors like that. Okay, actually I wrote this one. These problems was in the our discussion sections. So if you need the solution of these these problems, then you can see the solution on the discussion section videos. Okay, you can find it on the week 1 video. After that, we saw the equation of lines. So parametric equation of the line and parametric equation of the plane and the linear equation. Okay, actually we reviewed these concepts in the week 6.1 video to find the parametric equation of the tangent line of the parametric curves and tangent plane of the parametric surfaces, right? So I will skip the review of these concepts. But as you can see, there was the problem like of finding the parametric equation of the line through these 2 points. And find the parametric equation and linear equation, you need to know the difference of these two equations. And actually, I also talked about this one on the week 6.1 video. When you find the parametric equation of the tangent plane and the linear equation of the tangent plane. So you can find that problem. And actually, these problems was in the video week 2.1. Okay. After this one, we've talked about the limit of functions. So limit of functions, but we focused on the, the limit does not exist. We focus on the case that the limit does not exist. Actually, if the limit exists, then all these limits from different paths should the same. So using this concept, we saw that in this problem like that, if this limit exists, then all passes like this. This path is the x is changed, but y is fixed. It is y equal to 0. And this one is, x is fixed. So x equal to 0. And there will be the case like this path x equal to y. So in this problem, we check the limit of these curves, these paths, which converging to our given point 0, 0, and we compare the limits, and we can see that the limits are different, so this limit does not exist. Okay. And we talked about the continuity of the function. And if the function is given by like this, then to be continuous, limit of x, y goes to 0, 0 of the x squared y cubed over 2x squared plus y squared must be 1. Okay. And as you can see, elementary functions are continuous over their domains. So if a function is given by like this, then we need to check the this denominator can be 0. So we want to find the discontinuity point by solving the equation like that. This is equal to 0, like that. And also composition of a continuous function is continuous over its domain. So when we want to find the continuous point of this composition function, then we just define the domain of each function. And so it must be, t must be bigger than 0, so it must be bigger than 0, like that. And then we talked about the partial derivatives. So partial derivative is calculated by definition. You can calculate it using this limit here. So you can practice by solving some problems. And directional derivative is the partial derivative, like a partial derivative. We can calculate it using the limit. And also, if you know that f is C1 function, then you can calculate it using the gradient of f and our given vector v. One important thing is our v is a unit vector. And this gradient f is just the f1, f2, like that, fn. And it is the partial derivative with respect to its variable. So if we think about the x, y, z coordinate, then it is fx, fy, and fz, like this one. Okay, we can calculate it using this inner product. And if we think about the scalability function, there would be the level set of f. So as you can see in this problem, we saw that this f, the level set of this function f is given by, like this. Oh. Actually, this and this level set, and we can find the normal vector to our level set, and it is exactly the gradient f of our given point. Since our f is given by x plus 3y plus 5z, here gradient f is 1, 3, 5. You can see here. So so level set is, if our level set is given by like that, at this point our normal vector must be I think it is better to say that normal vector is parallel to gradient f. Parallel to gradient f. And we can find the tangent plane of a graph. So it is given by 1 point, and this is the tangent vector. This is also the tangent vector. So we can find the tangent plane of the graph. And we learned the chain rule, right? So I wrote chain rule 1 and 2, but the main idea are the same. So if you think the function z and z was the function of x and y, we just put x, y like this. And you can see here x is the function of t and y is the function of t. So we just put like this. And if you want to take a derivative with respect to t, then we find that there are two root. There are two paths. So we can find this formula like this one times this one plus this one times this one. But if you know this formula, then you don't need to think about this tree graph. Okay. If you forget the formula, then you can recover the formula by thinking about this tree graph. Okay, so we can take a derivative, and if you have one more variable, then you can do it in the same manner. And second derivative, yes. Here, there are many notations. Well, you can see that fxx is the take partial derivative with respect to x second times. So first we take a derivative with respect to x, and then we take a partial derivative one more time. fxy is the like this. And as you can see here, x is the first partial derivative, and then we take a partial derivative with respect to y. But there was the theorem that the fxy and fyx are the same as some assumption. Yeah, we need some assumption, maybe C2 function. That, so fxy and fy are the same in many cases, in most cases, because we deal, we talk about the very good functions. We do not talk about the real functions. So in many cases, fxy and fy are the same, and the theorem name is Claret. I'm not sure the pronunciation, but you can find it in the lecture note. Okay. And fyy is just the take a partial derivative second times with respect to y. Okay. And the Hessian matrix is the given by second derivatives like this. And we used Hessian matrix on the second derivative test. Okay. Critical point is the points that such that gradient f is 0. So by solving this equation, we can find the critical point. And second derivative test is useful when you think about the local minimum and maximum. Okay. So the determinant of the Hessian matrix is positive and the fxx is positive, then we can say that this point is the local minimum of f. Actually, we only need to check the critical point. Okay. And if the determinant of the Hessian matrix is negative, then we can say that this is the local maximum. And if determinative the sorry, I think this means that the fxx is bigger than 0 and determinant of Hessian matrix is uh, greater than 0. And the second thing is fxx is less than 0 and determinant of hfa is greater than 0. Mhm. But if our determinant is less than 0, then we can say that it is a saddle point. Okay. Cool. And let me see just a minute. I think it's better to check it. Because second derivative, because then just a minute. I think that's right. Mm, yes, that's right. And let's think about the min-max theorem. This theorem is for the global min-max. This second derivative test was for the local minimum and local maximum here. But if we want to think about the global minimum and global maximum, we want to use this theorem. It means that if this function is continuous where the closed and bounded set, then there must be the global minimum and maximum. To find the minimum and maximum, we first think about the critical points inside the domain. And then we want to check the value of f on the boundary. Actually, there are two methods to find the maximum and minimum of the function on the boundary. The first thing is just the think about the boundary by checking the values along the curve along the boundary. The second thing is using the Lagrange multiplier. Okay. So in this problem, our boundary is given by a rectangle like this. So we just find the minimum and maximum values on the boundary by checking the values on each line or on each rectangle, okay? And Lagrange multiplier says that if f and g are the function and we want to find the local minimum and maximum with the constraint here, then either gradient g is 0 or gradient f is equal to lambda times gradient g. So if we say that the gradient g is not 0, then gradient, this equation must hold. So, you know, we can find the points where the minimum and maximum is obtained by solving this equation. Okay. And if there is a vector valued function, we can find the divergence, and divergence is just the scalar. We can calculate it by, taking partial derivative at each coordinate. So let's say that f is given by this, given by like this, then we just take a partial derivative with respect to the first derivative, and this is the second coordinate, and we take a partial derivative with respect to second variable, and like this. It is the divergence of the f. Okay, and curl is vector. Divergence is a scalar, but curl is the cross product, so it is the vector. So curl f is, you can calculate it using this determinant of the 3 by 3 matrix. And one thing you need to notice here is f1, f2, f3 is not a partial derivative. It is just the coordinate functions, okay? And Laplacian is given by the divergence of gradient f, and you can find it using like this. Actually, if f is the scalar function in R3, then it is calculated like fxx plus fyy plus fzz. It is just the summation of all second um, partial derivatives. Uh, I mean, fxx plus fyy plus fzz. And we say that this function is a harmonic if this Laplacian equal to 0. And we said that f is potential function of this vector valued function if this vector valued function is given by gradient f. And this one is just the week 6.1 video, week 6.1 video. So I will skip the review of this concept. We solved that the finding equation of the tangent curve, and we find the equation of the tangent plane. And actually we find two types of equation. First type is the linear equation by using the normal vector, and the second thing is the parametric equation by using our TU and TV. Okay. Okay, I will stop here. Good luck, everyone.